So today we are talking about quantities in chemistry, and we're talking about a mole. It's not this little sucker who digs holes in your garden. We have pairs of shoes and everyday quantities like a dozen eggs, and we all know what they mean. When we speak about food, we don't speak about how much meat is in this hamburger patty, we just talk about one hamburger patty. It's a quantity. Or a packet of chips. We don't think about how many chips are in there, we just know that it's a packet. And these are examples of everyday quantities that we deal with and understand all the time. When we bake, we talk about flour by the cupful. Now, what is a cupful, or a third of a cupful, or a quarter? Here we've got a half a cup of oats going into a baking mixture. But how much is that exactly? We've got a cup full of flour going into the same mixture. But what is a cup? We mix it all together, we bake it up, and we eat the product. Here we are going to show 120 grams of butter. But what is 120 grams? We just accept that quantity. A tablespoon of syrup. By the way, we're making crunchies here. And here we're about to add a teaspoon of sodium bicarbonate, or what we call bicarbonate of soda. But what are these quantities that go into making this mixture that we then chuck in the oven and makes these very yummy crunchies? How much is exactly in this mixture? What quantities are we talking about? How much matter is represented by all of these things? Okay, so now that we've sort of got an idea of everyday quantities that we speak about all the time and that we take for granted, now we can start to talk about quantities of elements or compounds, so substances, and we can actually use it as a way of counting atoms, and we know how many atoms are present. But because atoms and molecules are so ridiculously small, it's impractical to talk about actual numbers of atoms or molecules, or even particles really. And remember, the particles are much, much bigger than an atom or a molecule. So the mole is a way that we can quantify those figures, but in a way that we can actually use the figures. So I've just got a few things here. I mean, I've got a big tub of sulfur and I've got some iron filings. So if we wanted to react these together to make iron sulfide, how would we know how much to use or how much we would make, right? So here's the yellow powder of sulfur. Now, I can't count every single particle of sulfur powder that's there. We've got no way. So what we do is we use mass. And now what a guy called Avogadro did is he looked at carbon-12, because carbon, we are all carbon-based life forms and carbon is essential for life. And he figured out how many atoms of carbon were present in carbon-12, and we use that number to signify how many atoms are present in 1 mole of any particular substance. So in 1 mole of, this is sulfur, and the most common isotope of sulfur has a mass of 32 grams per mole. So if we have 32 grams of sulfur, we know that we have 1 mole's worth of sulfur atoms present. So 6.022 times 10 to the power of 23. And we can use that figure to calculate any mass that we have. So this is half a kilogram. And we can do a very simple calculation to determine how many atoms of sulfur are present in this container. We can mass the iron filings, right? Just to prove to you that the iron filings, let's take a magnet, and you can see they're responding to the presence of a magnet and are held and attracted to the bottom of the container even when I turn upside down, so that is definitely iron. And we can mass this quantity of iron and determine how many atoms are present. If we reacted half a kilogram of sulfur with just a little bit of iron here, we would have way in excess of sulfur. So we could calculate how much sulfur we could use to react with this small amount of iron so that all of your reactants are used up. Okay? Those are the kinds of calculations that we are going to do this year. And that is what stoichiometry is all about. So there's no need to chuck all of this in with this little bit of iron. We can do a calculation and measure it out and work it out exactly so that there is no leftovers. Here, how much, this is zinc, right? So how much zinc have I got in this dish? Well, the only way we can calculate it is by determining its mass, by the way. So earlier I had iron, just to prove that not all metals react to the presence of a magnet, okay? So this is non-ferromagnetic metal, it's not responding to a magnet. But being zinc, we can mass it, we know what the atomic mass is from the periodic table, and we know that 65 grams of zinc will give you 1 mole of zinc, and we can use that, we can use an equation to determine how many atoms of zinc we have in this dish. The mole is just a quantity. It's just like, just like in the baking, and a pair of shoes and a dozen eggs and a kilogram of this and a teaspoon of that. It's just a quantity, and it tells us how many atoms are present, all calculated off the periodic table using the atomic mass. The atomic mass, if you take that number in grams, that will give you the mass of 1 mole of whatever atom you are talking about. And therefore, if you are talking about a compound, all you need to do is combine the various masses of all of those constituent atoms to calculate your molecular mass, and then you will have that many. So for example, water, you've got oxygen with a mass of 16 and 2 hydrogen atoms each with a mass of 1 each. So you combine 16 plus 1 plus 1 and you will get 18 grams per mole. So 1 mole of water will weigh 18 grams. And you can determine how many molecules are present merely by being able to determine its mass. And there are some other tools that you will learn about as we go along, but let's just start with using mass and calculating the number of mole and using the mass to determine how many atoms are present in whatever substance you have. Okay boys, so now that you have an idea of why we use the mole in chemistry, with the atom being, it's so incredibly small that we can't use the number of atoms or the mass of an actual atom. We can't use that in a real world calculation because it is so small. So what Avogadro did is he took carbon being essential for life, okay, we are all carbon-based life forms. So he knew that a single carbon atom of carbon 12, he knew it had an atomic mass of 12. So what he did is he took a workable quantity of carbon. He chose 12 grams, okay, because he knew the atomic mass was 12, so he took 12 grams. And he determined the number of atoms that were present. And that is where he got this number that we call Avogadro's number from. 6.022 times 10 to the exponent 23. So that is where that number comes from. So in 12 grams of carbon, we know that that's how many atoms of carbon there are. And it works the same for any element. So in our hypothetical reaction that I'm talking about today, we've got iron reacting with sulfur. Now iron has an atomic mass, or the most common form of iron has an atomic mass of 56 atomic mass units. So if we take 56 grams of iron, we know we therefore have 1 mole. Sulfur, atomic mass 32. Therefore 1 mole weighs 32 grams. Okay? And the little number n that I've got written up there, that is the symbol that we use to signify the number of moles. So in a in that mass, so if we take any element, right? So if we take oxygen, mass number 16, and we take 16 grams of oxygen, we know that we have that many atoms present. If we know how many moles we have present, we can therefore calculate the number of atoms. So let's take our hypothetical reaction that we are talking about today, and let's write it out. So we've got iron plus sulfur making iron sulfide. And then by writing it like this, we know that we're dealing with iron 2 sulfide, okay? Sulfur is in group 6 and therefore has an oxidation number of -2. So if we write it like this, it must mean that therefore iron has an oxidation number of +2. They both have 2 electrons available for bonding, and therefore bond 1:1, so we know it's iron 2 sulfide, reacting in a 1:1 ratio. So we know that in a reaction, hypothetically, if we've got 0.2 moles of iron, that we will need 0.2 moles of sulfur, and it will make 0.2 moles of iron sulfide, therefore. But let's work out how many atoms we have present in 0.2 of a mole. So now that we have our completely balanced chemical reaction, and we know that everything is in a 1:1 ratio, regardless of what we're looking at, we know what we can calculate. But everything is, in this calculation, everything is going to be 0.2, because we're saying that we're starting with 0.2 of a gram of iron as our known substance. So we can work out how many atoms of iron we have present. So let's write it out. We have number of atoms of, and we'll just say iron, and that will be, we know we have 0.2 mole present, and we multiply that by Avogadro's number, and that will give us the number of atoms that are present. In this case, we're talking about iron, and that will give you 1.2044 times. So that'll give you 1.2044 times 10 to the exponent 23 atoms. Now, even that's a crazily high number of atoms to have, right? We would never try and write that number out, and that's only 0.2 of a mole, 1/5 of a mole. So that's why we tend to use the mole instead of trying to count atoms. And then from knowing how many moles that we have, we can derive how many atoms. So the mole is a far more workable number than Avogadro's number. For today, please understand how to calculate the number of atoms if you are given the number of mole. And in later lessons, we'll start learning how to work with this variable, which is the number of moles. There are an extensive amount of calculations that you can do, which are all present on your data sheet. For today, though, you've just got to understand what the mole is, okay, and where Avogadro got this number from, and that number of atoms are present in 1 mole every single time that you are dealing with 1 mole of any substance. Understand that a mole is merely a quantity that we can work with in chemistry, okay? It's something that we can see and that we can, without having to use a microscope. And we can determine its mass using a normal scale that we would have in a laboratory. So it is just a representation of quantity, and that we can do this calculation to calculate how many atoms are present. And then join for the next lesson, we will start learning some of the more complicated calculations where we deal with this variable little m.